Welcome, everybody. Very happy to continue this series. And today's speaker is Martin Lemoine, who is a senior CNRS scientist at the Institute for Astrophysics in Paris. Martin is very well known for his work on astroparticle physics in general, and in particular on collisionless relativistic shocks and particle accelerations and this collisionless relativistic shocks. So this is the topic of his talk today.
So thank you. So should I share? Okay, so it should be fine now.
Looks good.
Yeah, thank you. So please let me start by thanking really heartily our host for putting up this virtual institute and for organizing this series of lectures that I'm really looking forward to. And I'm also, I should say, I'm also very happy to be part of this adventure, and I hope it will be very productive, and I really enjoy it so far. And I should start maybe by mentioning some of my long-term collaborators in France. So, particularly my students, Virginia Bresci, who's currently a second-year graduate student at IAP, Camilla Demidem, who graduated in 2019, who's now a postdoc at Nordita, and Arnaud Van Tighem, who's graduated also in 2019, who's a postdoc at Stanford. And also my long-term collaborators, Laurent Grémillet, more senior, and Guy Pelletier. And I would like also to acknowledge some ongoing work or past work with the people here, which as I understand, are all part of this institute, this CDY Institute. And so I thought that I should tell you, share some thoughts and some results on particle Fermi type particle acceleration in relativistic outflows with you. And the way I would like to organize this lecture is as follows. So I would like first to start by giving you some very general remarks on the relativistic Fermi acceleration. So just to set up the stage for something which is maybe a bit more new, which is on the physics of particle acceleration in complex velocity fields or in turbulent flows, and which contains some new results. And I think these new results are somewhat a bit more specialized, I should say, than the first part. But there are some interesting connections with recent particle in cell simulations, and they will actually, I think, set up the stage for an interesting discussion that that is supposed to follow the lecture. So just to make sure that we all talk about the same thing, what I mean here by Fermi type acceleration is, of course, those scenarios that take place on time scales sufficiently large that in the local plasma rest frame, any electric field has been screened out, so that what actually subsists and what can give rise to particle acceleration is a so-called motional electric field. That means the electric field which is carried by the moving magnetized plasma. And so it is given in standard case by ideal Ohm's law, where Vp is the plasma velocity. And those Fermi type scenarios, the prototypical examples are, of course, the original Fermi scenario in which a particle gets accelerated by repeated encounters with moving magnetized scattering centers, or the shear acceleration, in which I will come a bit later, or of course the one that maybe we know best, which is particle acceleration at shock waves. And as a matter of fact, I will not talk about particle acceleration at shock waves. I will talk mostly about the first two, so particle acceleration in complex velocity fields that includes shear flows and turbulence. And I will not address at all particle acceleration scenarios in non-MHD flows, so so-called linear accelerators that take place in gaps in the vicinity of compact objects, or maybe even reconnection. Even though, as you will, I hope I will not forget to mention it, but reconnection is now understood to play a key role in injecting particles in Fermi type scenarios in these complex velocity configurations. And maybe to illustrate more what I would like to talk about, I I took this beautiful banner from the homepage of this host institute. And here, if you take one of these objects that is illustrated here, for instance, the galactic center, so Sagittarius A star, then this is an image of a numerical simulation of a GRMHD that shows the flow in which particles can get accelerated. And one of the recurring themes and ideas that I would like to develop here is the fact that, or stress, because it's well known, is the fact that a particle is sensitive to flows that are organized on scale comparable or larger than its mean free path, or at least its gyro radius. And that means that if you take a particle and you inject a particle in this velocity flow, and then it starts to get accelerated by some Fermi mechanism, then at first, because it has a small energy, therefore a small mean free path or small gyro radius, it will actually experience this accretion flow turbulence as some kind of large-scale turbulence. And then what you will be dealing with is particle acceleration in a turbulent flow. But then as the particle in energy further increases, eventually the mean free path of the particle will become comparable or larger than the scale of this turbulence. And then what the turbulence will actually see in terms of accelerating engine is rather the shear of the velocity flow inside the accretion disk. And then it will suffer something which is closer to shear acceleration in a disk. And then, although we're already talking here of very high energies above a PeV in general, as the particle energy keeps increasing, then it will actually become sensitive to further and larger scale velocity flows until it eventually escapes from this system or maybe enters the jet. And I think that's a point to keep in mind, especially given that in nature, the hierarchy between the macroscopic sizes of the sources that we are dealing with and the microscopic scales on which the particles are injected, or the scales of kinetic plasma physics, this hierarchy is so large that you are really dealing with a very broad range of scales. And to take another example that some of the people here know very well, is the fact that when you study particle acceleration inside jets, then some of the scenarios consider the particle, for instance, is injected at some shock inside the jet, but then it will be further accelerated because it travels inside some turbulent plasma which permeates the jet, and possibly some shear acceleration inside the jet itself. And also, I think that one thing that I would like to mention is we all have in mind this idea of, and this picture of a beautiful, neat shockwave in which particles are accelerated. But as we study the universe in more and more details, what we see is actually some sources that have a more complex velocity pattern, maybe, and there are scenarios of hierarchical Fermi acceleration that are developed, in which particles are injected by some accelerating engine on some scale, then they get accelerated to some higher energy, they escape that engine, and then they can enter another acceleration scenario, and so on until they reach very high energies. And that will probably be something that Tony Bell will mention in his lecture, coming lecture. So this is the pattern that I have in mind in setting up the stage for this framing this lecture. And indeed, when you talk about Fermi acceleration, the key point about Fermi acceleration is really how the particle travels through the turbulence. And this is a point, it's well known, but sometimes, at least in phenomenological application, it's sometimes overlooked. And the reason here is the following, is that because the electric field that accelerates the particle is a motional electric field, it means that it is perpendicular to the magnetic field. Therefore, if you want a particle which is tied to a magnetic field line to effectively get accelerated, then it needs to scatter to be able to do some cross-field transport and explore the configuration. And one way to classify those acceleration scenarios is first of all, the topology of these electric fields, which is the topology of this electromagnetic configuration, but most of all, how the particle will travel through this configuration. And let me now show you why this is so important. That if you take the prototypical Fermi acceleration scenarios, except maybe shear, to which I will come back in a minute, then the generic scaling for the acceleration time scale is that it scales like the scattering time scale. And the acceleration time scale is really what controls the phenomenological application. As you know, if you want to know the maximal energy that you can reach, then you will compare the acceleration time scale to other relevant time scales, such as the energy loss time scale or the escape time scale, etc. And then you will find the maximum energy until which you can accelerate particles by setting those time scales to be equal one to the other. And you see that the scattering time scale really controls the acceleration time scale because the particle has to scatter in order to be able to experience the electric field. This scattering time scale is the mean free path, if you want, divided by the velocity of the particle. And in principle, you can express it if you are traveling into some turbulence that supports this scattering. Then you can express it as some power law dependence on the Larmor time of the particle, TL, which is directly proportional to the particle energy. And in most phenomenological application, people will invoke the Bohm regime. So that's alpha 1. So that means that the scattering time scales as the Larmor time. And in that case, the particle, so this is here on the y-axis, the ratio of the scattering time scale to the Larmor time. So that means that here it's unity. And this is plotted as a function of the Larmor time, or if you want, as a function of energy. But there is a particular point in this diagram, which is when the gyro radius becomes comparable to the coherent scale of the turbulence. Because as it turns out, we know pretty well the physics of transport on scales larger than the coherent scale of the turbulence. Because in that regime, we can set up some perturbative scheme, and it is well known that the scattering time scale increases as the square of the Larmor time. So we can have this line, and then we can try to extrapolate backwards what should happen. And this is where it becomes a bit more confused, and we don't really know what to expect. So the Bohm regime really is an assumption, but this is an assumption that is motivated by the fact that we are trying to look for extreme accelerators. But it might very well be that in nature, the transport is not as efficient, and that the ratio of the scattering time to the Larmor time would, as a matter of fact, increase as the energy decreases here. And the consequences are as follows. So you can define three regions in these diagrams. So the first one is the Bohm regime. So as I said, the Bohm regime, so if you are dealing with relativistic outflows or relativistic motion, then you can set the effective velocity of your scattering centers to be close to c, so that the acceleration timescale is of the order of the scattering time. And so if you write it to simplify notations, this ratio of scattering to Larmor time as A, this factor A, then you can, as is very well known, you can show that the maximum synchrotron photon energy that will emerge out of this accelerator is close to the radiation reaction limit up to this factor A. So this is the regime of extreme lepton accelerators. But I would like to stress the difference here is that you also have another regime, which is perhaps more common, at least from the theoretical point of view, which is that of extreme ion accelerators, because and that this regime 2, in this regime 2, this factor A can take values much larger than unity. But the point is that in this regime here, the scattering time still increases with the Larmor time until the particle eventually reaches the coherent scale of this turbulence. And if the coherent scale of the turbulence is close to the source size, if you're in the relativistic regime and say the magnetic field is sufficiently disorganized, then you can reach a regime in which at this point, the scattering time scale which will be of the order of LC. And therefore, the particle will be able to reach the Hillas limit. And the Hillas limit here is the extreme ion accelerator. So this is directly relevant for very high and ultra high energy cosmic rays, of course. And the third regime is that which I discussed previously, is when the particle energy becomes even larger, so that the gyro radius of the particle becomes larger than the coherent scale of the turbulence, then it effectively decouples from the turbulence. It becomes weakly sensitive to it, and the scattering is very slow. And so all this will be relevant for the discussion that I will come to at the end of this talk. And so to illustrate the role of the scattering, let me now turn to the physics of shear acceleration. So shear acceleration is a very interesting acceleration scenario, notably because the scaling that I showed you here, the acceleration time scale versus the scattering time scale is different. And I will explain why in a second. And in shear acceleration, so the prototypical shear acceleration scenario, which I draw here, is say, for instance, for a jet. So on the right and on the left, the electric field is 0. You're outside the jet. But inside the jet, the velocity field has some maximum. Then it decreases back to 0. And there is a out-of-page magnetic field here. And that gives rise to this motion electric field whose strength and orientation is illustrated here. And I consider 3 different cases here. On the left, this is when I have a small mean free path. So this is illustrated. The trajectory of the particle is illustrated by this red arrow. So I have a very small mean free path. And mean by small, it is relative to the length scale of the shear, which is given by beta E divided by the shear of beta E. And then on the middle, you have a more or less resonant case in which the mean free path is comparable to the length scale of this gradient. And on the right, this is where the mean free path is much larger than the length scale of this gradient. Then if you go to this nice paper by Frank, you will see that it is explained why in this limit, the acceleration is very slow, which is very different from the previous cases of Fermi acceleration, because in the previous cases of Fermi acceleration, the acceleration timescale is a growing function of energy, which means that acceleration is very fast at small energies, and then it becomes even slower and slower as the particle energy increases, because of course it scales as some function of the gyro radius, which increases with energy. Here, this is the opposite, meaning that at a small energy, the acceleration is very slow. When you are resonant, acceleration is optimal, and then when you have an energy which is very large, then this is when the particle effectively decouples from the flow, and then you have a very little acceleration. The reason why it's very easy to understand in this case, this is because if you say that the mean free path is much larger than this gradient, then the particle starts from a configuration in which E is equal 0, then it ends up with a configuration in which E is 0, so it effectively doesn't see any electric field. And this is also similar, as a matter of fact, to what happens in reconnection studies, where you say that in reconnection layers on very small scales, then as long as the particle's gyro radius is comparable to the size of the reconnection layer, it can be very effectively accelerated. But once the particle energy becomes sufficiently large, then the particle flies through the reconnection layer and it hardly receives any kick in energy. Now let me turn to this regime on the left, because it's an important case. And what happens here is the following. If you, I plotted the trajectory of the particle at this location, but I could have plotted the particle trajectory at this location where the electric field reaches the maximum, and my conclusions would not have changed. And the reason is the following, is that if the mean free path is very small compared to the scale of the gradient, it's similar to say that when you zoom in on the scale of the mean free path, your gradient is actually very weak. If the gradient is very weak, it means that in a region in which I have a small gradient, then my electric field is roughly constant. Therefore, I can boost to a frame in which this frame, which moves at velocity beta E, in which this electric field vanishes. And as the electric vanishes in that frame, I have no acceleration, because in that frame, the particle will be undergoing helical orbits around the magnetic field line. So the true reason why particle gain as energy is because it is able to interact with the gradient of the electric field. And the fact that there is a gradient guarantees that the electric field cannot be boosted away everywhere in the plasma, so that there is some location in which there is an electric field to accelerate the particle. This is exactly what you have in shock acceleration, because the discontinuity in the velocity flow, which represents this shear or this gradient of the velocity, guarantees that whatever the frame you pick, on one side of the shock or another, there will be an electric field and the particle will be able to be accelerated there. And this is how you can understand the peculiar scaling that you have for the acceleration timescale in shear acceleration. You have this 1 over beta E squared. This is typical of Fermi scenarios. I will not come back to that. But what I'm interested in here is this scaling, which is inversely proportional to the scattering time scale. And what you have here is the length scale of the gradient. And you see that L squared divided by T, or by the mean free path, really characterizes the time it takes to explore the length scale R, the length scale of the gradient, in a diffusive manner, undergoing a random walk with some step given by T scat. And the last remark I would like to make here before moving to my second part is the fact that when you discuss shear acceleration, most often you assume that there is a source of scattering, of course, but you neglect the influence of this source of scattering, which is turbulence, on particle energization. So in some way, this shear acceleration scenario is also idealized. So you assume some scattering, but you do not discuss really what the source of the scattering and the impact of turbulence on particle acceleration is. And when I would like to discuss the case of a more complex velocity flow in which those effects are intertwined. And really what is important here is what matters when you are discussing the physics of particle acceleration in those Fermi acceleration in those velocity flows, as I've tried to convince you, is the gradient of UE. UE is this E cross B velocity, but I write it UE because it is, in my mind, it is a 4 velocity. So we are really in relativistic Fermi scenarios. And again, this is because the fact that there exists a gradient guarantees the fact that there is somewhere an electric field that can give rise to acceleration. So when you have a shear tensor, you can decompose it into various contributions which are related to compression of the flow or the dilation of the flow, the shear itself of the flow, which we just discussed, but also the vorticity and the acceleration itself of the flow. And you see, if you recall what happens in collisional fluid dynamics, so you take a particle, part of a fluid, so, and then you compress that region of the fluid. Then you know that this is adiabatic compression that will hit the plasma. This is because you assume in this fluid frame, in this fluid dynamics framework, that you have some effective collision operator that will effectively reorganize the momenta of the particles. What happens in those collisionless plasmas is that this is the scattering that does the job of the collision. And the particles, if it is inside a compression flow, then because it scatters on those magnetic configurations, it will also be heated, so it will be energized. And this is how compression, this is the collisionless analog of this compression effect on particle energization. And as I note here at the bottom, one way of understanding this is, or seeing this, is really as a generalization of the original Fermi scenarios, which considers interactions with moving discrete clouds considered as magnetized scattering centers to a continuous flow. And now I would like to apply it to the case of turbulent flow. So what you have on the left, really a cube of turbulence. And this is the basics of one of the papers that was suggested as reading here, which is a paper I published in 2019, in which I defend the idea that in order to quantify this, the best way to do it, to describe this physics of Fermi acceleration, is to follow the particle momentum in the frame in which the electric field vanishes. This is what people who work in shock acceleration know this very well. This is what they do when they write the transport equation. And this is here a convenient choice also for turbulent acceleration, because it allows you to relate the gain of energy to the shear of the velocity flow. And the reason for this is the following, is that in that frame where the electric field vanishes, then the particle cannot receive any energization from the electromagnetic field because there is no electric field. However, the fact that there exists a shear of the velocity field guarantees that this frame is an accelerated or non-inertial frame, which means that there exist some inertial forces that act on the particle in that frame. And when you write the gain of energy for the particle in that frame, then this gain on energy scales like those non-inertial forces, and those non-inertial forces are directly related to the shear of the velocity flow. And then the various ways in which you can use this description to tackle Fermi acceleration scenarios. And in that first paper in 2019, I showed how if you assume some isotropic scattering, some mean free path, then you can recover what I showed you a couple of slides ago, this scaling for the acceleration time scale. Here, what I would like to do in the second part is to apply this to the case of particle acceleration inside turbulent flows. So what I will do is that I will go deep inside the inertial range of turbulence. That means that the particle energy will be sufficiently low that the gyro radius of the particle is very small compared to the size, the coherent scale of the turbulence. In that case, you do not assume isotropic scattering. You need to assume that a particle is undergoing a local gyro motion around the magnetic field line in this frame in which there is no electric field. And if you do so, then you break the contribution to energization. Yeah, this is the variation of the Lorentz factor of the particle in that frame, into three contributions. And those three contributions, they are inertial forces. So before I describe those inertial forces, let me give you 2 points of view. One is the standard one in which you are in the laboratory frame. You have motions of the plasma. This is Fermi acceleration. So those plasmas, they're carrying moving elements of plasma, are carrying motional electric fields. And as the particle can interact with those electric fields, it can gain energy in a stochastic manner. Now there is this other picture here in which I move to the frame in which there is no electric field. There is no electric field, but here this is a non-inertial frame. So you can picture the particle tied to this magnetic field line, and here it gets kicked in one way or another. I'm talking about its energy because the plasma is moving. So that gives rise to acceleration, and the acceleration of the plasma projected along the field line gives rise to an effective gravity that accelerates the particle, of course. But also as the particle travels along the field line, it can see the shear of the velocity field along this field line, and then it can suffer effective shear acceleration along the field line. But also my particle is undergoing helical motion around the magnetic field line, so it is effectively tied to that magnetic field line. And if I compress the plasma from the sides, so transversely to the magnetic field line, then I will squish in these field lines, and I will hit the plasma and energize the particles. So that are the three terms that contribute to energization. And in the following, I will compare this to simulation to show you that it provides a realistic picture of what happens in those configurations. One clear advantage of this formalism is that I have a clean formulation of the gain of energy for my particle as a function of quantities that directly depend on the direction of the magnetic field line. This is the B here, the 4-vector B, and the 4 velocity of my plasma or my field lines. And therefore, I can go to some simulation, for instance, an MHD simulation. Here, this is an incompressible MHD 3D simulation, which is available for public use from the Johns Hopkins database. And I can directly image in that simulation my accelerating centers. What I will show you here is these terms theta perp, which is a compression transverse to the field line. And I plotted them in blue where they are positive and in yellow where they are negative because of the sign that comes here. So if theta perp is negative, it gives rise to energization. If it is positive, it cools the particle or takes energy away from it. And there is a very interesting picture here is that as the particle travels through the plasma contains those regions in blue and white, but they only occupy a small fraction of the turbulence. And that's a very different picture from what we have in mind usually, in particular when we do quasi-linear calculations where we assume, where we assume that we have a homogeneous bath of waves. And also is the fact that the acceleration is proportional to the gradient of this 4 velocity UE. And this 4 velocity UE itself is related to the magnetic field, tells you that you should expect, and this is what you see here, is that those acceleration regions, they are located in regions of gradients of the magnetic energy density. This black to white here is the magnetic energy density of the plasma. And you see that in regions of extrema of the magnetic energy density, I have 0 acceleration sites. And this is also very unlike what we have in quasi-linear calculation, where we directly relate the momentum diffusion coefficient to the magnetic and turbulent magnetic energy density. And finally, even though this picture seems a bit reminiscent of what you have from the original Fermi scenario, where you have a particle that sees some discrete moving clouds of a magnetic field, the physics is, as a matter of fact, it is different, because whether the particle gains energy or loses energy is not whether it will have a head-on or a tail-on collision with a moving cloud. It's just whether it will see a blue or a yellow region. So that's really characterized by the size of the shear or the compression tensor. And here, just for fun, I show you an animation. This is the same simulation because it's 10 to the 1024 to the 4. They have 1024 time steps, so you can image those acceleration sites as a function of time. And you see that on small scales, those are, you see this is in units of the coherent scale of the turbulence. On small scales, you have those regions that are really transient. Some of them are long-lived and they move slowly. So let me show you now the view from particle in cell simulations. So you can run particle in cell simulations in which you stir up the plasma, you create this turbulence. So I don't have the references here, I will put them later. But this is a particle in cell simulations that my student Virginia ran in our group. So this is a 2D particle in simulations of driven turbulence in the relativistic regime, meaning that the Alfvén velocity is close to c. This is time in units of the coherent scale of the turbulence. And what I will show you is how particles get energized in this turbulence. So those are the green dots, and the size of the dot is proportional to the energy. And look in particular at this particle. You will see that it tends, and others as well, tends to be energized in regions of gradient of the magnetic energy density, just like I said before. This is not, and you can see when the particle travels through a region of an extrema of the magnetic field, nothing happens to it until it reaches those boundaries regions where it starts to get energized. And you can see, using those particle in cell simulations, you can see in some locations you have some reconnection layers, and those reconnection zones, you have one here, for instance, those reconnection zones tend to inject particles inside into the non-thermal tail of the population. Here is another reconnection layer, but I did not place any particle there. So they tend to inject particles into the non-thermal tail, but they do not, that has been shown by other authors, they do not contribute much to the energization away from the thermal tail. And what I've shown you here really relates to the Fermi process, because I started with energies that are 3 to 5 times thermal, and I went far into the non-thermal tail.
Sorry, Martin, may I ask a quick question?
Sure.
Can you say what was the driving of that turbulence and whether you see large-scale current sheets here?
So, what was the what, sorry?
Driving, how did you excite the turbulence?
Oh, okay. So we use the scheme of the Colorado group, so that we use some random antennas inside the turbulence. So these antennas inject external currents in X and Y.
Okay, and do you see then current sheets of large scale?
So we do, so I don't know what you mean by large scale. So we do see some of them are large scale, so I don't know where they are. Some of them are very localized. So that was a very localized one. And I think that somewhere here there should be, yeah, there is a large scale one.
No, I mean, do you see magnetic reconnection in current sheets of large scale in this turbulence simulation? Like, do you see actually magnetic reconnection as energizing mechanism being important part of energy gain rather than stochastic acceleration in turbulence?
Okay, so I will come to that. So, but the standard law. So I don't know if you're referring to your paper on radiative simulations or the paper of Luca and Lorenzo. But then their claim is that really reconnection is the injection mechanism. So away from the thermal core, and then as you go up in energy, then reconnection plays a a lesser and lesser role because the particle gyro reduces, becomes large and large, and then the particles effectively get accelerated by E-perp, not E-parallel. So let me come to that. So what we have also done here is that we have compared, tested our scheme against those simulations, that will answer part of your question, I hope. And the way we do this is that we follow in this simulation the history of the momentum of the particle. And we also, at each point of the history of that particle, we compute those gradients of the velocity field. Then we use our formula to reconstruct what should be the energy gain. And we can, in this way, compute a theoretical history for the momentum of the particle. And then we have two histories, one predicted and one observed for each particle. And we can compute the correlation coefficient between those two histories. They are stochastic trajectories. And we can do that a large number of times with many, many particles. And then we end up with some histograms for those correlation coefficients. And you see that with this model, the correlation peak, and those are for two simulations, one is peak, the other is MHD. And for those two cases, we speak close to a very large correlation, which means that we can reconstruct satisfactorily, not fully, of course, the dominant contribution to particle energization. And also when it is broken down in terms of individual component, it seems to indicate that the parallel shear along the magnetic field line is the dominant acceleration mechanism here. And maybe to answer again part of your question, so those are the works that studied first those mechanisms of particle acceleration in turbulence. And what they see is that this is again a peak simulation that we ran, but whatever. You see that the red curve is the energy spectrum as a function of Lorentz factor of the particle. And what they see is that when you start initially, then you have you start with some thermal core. And then as time goes on, I will show you an animation, then you will develop a power law tail for the spectrum. And inside the power law tail, the dominant acceleration mechanism is comes from the perpendicular electric field, which is indicative of Fermi acceleration. Now, I should say that the nature of this Fermi acceleration, as I described it in the model above, I do not specify here what is the origin of this shear of the velocity flow. So if you could imagine that you have here it says that you have compression transverse to the magnetic field line or along the magnetic field line, which is a way of expressing the fact that the magnetic field line is curved. But what truly causes this shear of the velocity flow could well be the vertical motions of the eddies, or even the appearance of current sheets, because they form strong gradients on small scales. So let me show you this animation. I think it's very instructive, and it's a very important finding of those particle in cell simulation, is the fact that they contradict the standard model of the Fokker-Planck equation, which is used nearly everywhere in the literature. And you see that what you have here in dotted line is these Fokker-Planck prediction. So this is the standard Fokker-Planck equation. It depends, and the spectrum in that case is fully characterized by the diffusion coefficient. And here, let me go back to this simulation. You see that the two coincides at early time, because I have measured the diffusion coefficient in that simulation, and therefore it is tailor-made to reproduce the spectrum at early times. But as you go in time, as acceleration develops, then there is a transient stage, and then you see this power law that appears in the particle in cell simulation, whereas you have this Gaussian shape in log p, which is typical of stochastic acceleration as described by the Fokker-Planck equation. And this is understandable because those simulations, at least, the prediction is understandable, because you see those simulations, they are like a closed box. And Fermi acceleration really, when you shape a power law, when you end up with a power law spectrum, the standard interpretation is to say that you have a competition between energy gain and escape, or energy gain and loss. But whatever, you have a competition with energy gain and something that takes away the energy. And here you don't have this because this is a closed box. So of course you expect that as time goes on, then you give energy to the particles, and then their distribution will shift to larger and larger momenta, as predicted by this Fokker-Planck equation. And this is not what happens. What happens is that the energy that you gain will shift the peak of the distribution, so the thermal core, because it hits the plasma, mostly through reconnection type processes. But then you end up with a non-thermal tail, and this non-thermal tail, as we discussed it with Misha Malkov, is indicative that you have some segregation ongoing in the population of particles. And this segregation is the fact that some particles get accelerated, others do not get accelerated because of the time. So the issue here is the time that you are available. I'm not saying that the simulations are not long enough. You see, this simulation has run over nearly 17 times the coherence scale of the turbulence. I'm saying that this is really a true effect. And to understand this, I come back to this model and this picture. You see that the particles, as they travel through the turbulence, they see only very localized sites of acceleration. And therefore, the mean free path to interaction with those sites can be effectively quite large, of the order of scale of the coherent scale, or even larger for some of the particles. And this is what will give rise to the power law. And to show you this, I'm close to concluding, but to show you this, you can write up this random walk model. So usually what you would say, at least in the original Fermi scenarios, you would say, I have an interaction time, which is the step, the size of my cells, say, divided by their filling fraction. That's the mean free path to interaction with those cells. Then that's the step of my random walk, and I can see what happens on late times. And if I hit a yellow cell as before, I gain energy. If I hit a blue cell as before, I lose energy. But if you were to do so, that's really the standard process, then you would miss what happens on intermediate timescales, because you would already be discussing asymptotic timescales. And given the fact that this interaction time is macroscopic, then you would be actually missing the physics. And so to show you this, what you need to do is to work out this random walk, where for most of the steps, the particles do not experience anything. But some of the particles will be lucky enough to see many of those sites and gain energy. And when you solve that random walk, which is not trivial, as a matter of fact, when you solve it, but you can have an analytical expression for that random walk, then what you find is that the spectrum has indeed a Gaussian core. So this is really the standard Fokker-Planck type solution, but it doesn't fall off exponentially. It has a power law tail. And that power law tail captures the outliers that were lucky enough on the time scale that you gave them to encounter sufficiently many eddies, active eddies, to get energized. And so I won't discuss here the dependence on the model parameters. I just want to say that you have this power law, and that the slope of the power law evolves in time, just like in the particle cell simulation. It tends to harden in time. And of course, if at each interaction you give a bit more energy to the particle in one simulation, then you will end up with a harder power law. This is what illustrated here. And what I would like to show you now is that you can also capture there is also an analytical formula here for the spectral index, and you can capture the spectral index. So here, these units here is the acceleration time scale. So this is the standard expression for the Fermi mechanism. But the important point is that this is the acceleration time scale for the average of the population. And when you do that, you do not discuss properly the physics of the mechanism. Because when I say an average over the population, then I take, in this average, I have many particles that do not experience acceleration, and a few particles that experience very fast acceleration. As a matter of fact, you should describe it as a distribution of timescales, and that distribution typically has a power law shape. And that explains the appearance of the power law. And here I show these various spectral indices for different gain per interaction, so 0.3 to 3. And in relativistic turbulence, this should be of the order of unity. And so you expect a spectral index of 3, which is a bit what they observe in particle in cell simulations. So maybe it's late, so I would like to move to the summary and maybe open up the discussion or answer your question. But so let me summarize what I'm trying to say here. Is that you can describe this particle acceleration in this complex velocity flow as some form of non-resonant interactions. So this is different from the more traditional wave-particle resonant interaction picture. So this is really a non-resonant acceleration where particles gain energy from the interaction with a sheared and compressive velocity flow on all scales above its gyro radius. And as I showed you here, deep in the inertial range of turbulence, then the main energization mechanism is the shear along the magnetic field line and the compression transverse to the field line. And the important result, which was observed in particle in cell simulations and which is supported by this model, is the fact that because you are dealing with gradients, and because the gradients, the power of these gradients peak on small scales in turbulence theories, then that means that your intermittency is a key player here in the acceleration scenario. And this is a novel feature which has a very interesting phenomenological consequences. Usually, intermittency is regarded as something curious in turbulence, and it is understood in terms of higher order structure functions. But here, in terms of acceleration, it has the leading role because it is the feature that will shape the acceleration spectrum, accelerated particle spectrum. I also argued pretty quickly, though, that you can obtain a fair reconstruction or fair comparison of this model with particle in cell simulations, both in terms of this microscopic picture of particle energization and in terms of reconstruction of particle histories on a statistical basis. And so let me mention some things that I think are very interesting here, some possible consequences of this picture of turbulent acceleration. So as maybe if I wasn't clear, it has appeared in particle in cell simulation, and here I've tried to provide some interpretation and analytical explanation or model for this. So one very interesting point here is that the spectrum that you see in those numerical experiments is very different from the standard Fokker-Planck prediction. And I think that's a very interesting result because it opens a new window for phenomenology. So what will be the impact on the models for sources? And what will be the impact of how you understand shear acceleration in large-scale jets, for instance? And you see there is a very strong difference which needs to be pointed out with respect to the standard Fokker-Planck equation. Now, the standard Fokker-Planck equation doesn't pay attention to energy conservation, meaning that in the Fokker-Planck equation, the mean of the distribution drifts about as fast as particles get accelerated. That's because you assume that the turbulence is homogeneous, and therefore all particles roughly undergo the same history. They all get boosted to very high energies. But if you let this evolution last for some time, then the energy that you have transferred into the accelerated particle population is momentous. And that is not very well motivated for most scenarios of interest. Here, by contrast, the drift of the particle population is pretty slow, and it's directly related to particle injection, meaning that you inject energy in the plasma, it is dissipated on small scales after cascading through the turbulence that hits the population, but then there is some non-thermal tail that develops. And one thing that I would like to do is to try to improve this model, the model that I showed you, maybe to find some recipe to include it in numerical simulation that would be able to go to larger scales. Because as useful as they are, those particle in cell simulations, they always remain limited in their dynamic range. And the fact that you always have, say, a couple of orders of magnitude between the macroscopic scales of the coherent scale and the dissipative scale is really a limit, because in reality, those can be 6 or 10 orders of magnitude. And because this is not exactly a power law, but a quasi-power law with some logarithmic running of the spectral index, you could have some interesting effects there. So that's really about extrapolating this to large hierarchy also. And also, of course, and there are already some particle in cell simulations on this, is that you would like to understand how this all depends on magnetization, on the physics of the turbulence, whether you stir it in a compressive way or whether you stir it with, say, Alven-like modes, etc. How it depends on electron, whether it's electron-electron or electron-positron, sorry, or whether it's electron-ion plasmas, etc., with obvious consequences. For instance, you know that the physics of particle energization in turbulence of electron-ion plasma is really a key parameter to understand the physics of accretion disks. And finally, maybe even broader applications is the fact that if intermittency has such a role for particle acceleration, then it is bound to play a role for particle transport. And particle transport then affects many fields of high energy astrophysics. In my view, this is the first experimental indication of anomalous transport in those turbulence. There have been several papers over the years about the possible consequences of anomalous transport, but without clearly an experimental probe of this, it's difficult to, because parameter space is so large, it's difficult to make conclusive, to draw some firm conclusions. So here, I think there is something very interesting to study. And I will show you now a couple of slides in which I plot some figures. Also, the fact that on a time scale of the order of the coherent scale, then in those turbulence, only a small fraction of the particles are scattered, because those sites that give rise to particle energization, they also contribute to scattering in this model. And that means for most of the particles, they will go just in a straight line, not see anything special, and not scatter. And so that should give rise to anisotropies, which hopefully will be of some interest to cosmic ray physicists. Then there are some very interesting possibilities that emerge, is the fact that because this setting is very intermittent, it means that you cannot, if you take one volume of coherence, so LC cube, then you cannot say that everything will be statistically homogeneous. It will be all time dependent. You will have some anisotropy. You will have and that will give rise some flaring and a strange radiative spectrum. Of course, if you consider a region which is much broader, much larger than the coherence volume, then all this should tend to smear out. So let me show you just, let me skip this and let me show you this, for instance. So this is point 2, as I said, is the dependence on the physics of the turbulence. And this is an electron-ion simulation at low magnetization. So that's an Alven velocity of, say, 0.1, 0.15 C. And here, this is Alven-like driving of turbulence, compressive driving of turbulence. And this is for same, but for electron spectra. And you see that depending on how you stir the turbulence, the results are not the same. So, and by the way, you see also that the index of the power law here is -4, so it's pretty steep. And this is directly related to the fact that you're in the subrelativistic regime. And in the subrelativistic regime, as I mentioned, the energy gain per interaction is weaker, and therefore the spectral index will be, the spectrum will be softer. Here I would like to show you this, is that you know that when we talk in terms of particle transport, we usually treat the particles as a bulk. So we say that for one given energy, I will have one scattering time scale. Well, this is for one particle energy. I plot the distribution of the scattering time scale of the particles. You see that it covers more than an order of magnitude. And on the time scale of that simulation, this is the JHU simulation, on the time scale of that simulation, it was impossible to see that to see all the particles scattered, meaning that some of them, say 5 to 10% of them, still had not scattered after a time which is of the order of 5 or 6 LC/C. So that should clearly give rise to strong anisotropies on scales that are not negligible in some sources. You see that plot that I showed you before? This is the ratio of the acceleration timescale divided by the Larmor time as a function of the Larmor time with those various regimes. And then you can compute whether you will see a synchrotron radiation up to the radiation reaction limit. Well, the connection to this new picture in which this is also intermittent is not straightforward, because in one region, say where it is dark here, you will have a local radiative spectrum shaped by the distribution function in that region, the velocity that gives rise to the boost, to the Doppler factor from that region, and the magnetic field strength, which is also inhomogeneous in those settings. And then in that other region, you will have another spectrum. And then the spectrum that you will see from the cube will be the sum of all these different spectra. And to show you some illustration from particle in cell simulation, this is one here, where you have two regions, A and B. And in this region A and this region B, you don't have the same particle spectrum. So this is one illustration of intermittency. Another illustration here is from that particle in cell simulation, where they plot the anisotropy of the momentum distribution function. And you see that there is pretty strong anisotropy, which implies that there will be, because of those beaming effects, whether you're on the line of sight or not, you will see some flares from those simulations. And I think I should stop here and just let this open maybe for a discussion. So thank you.
Okay, thanks very much, Martin. Questions, please. Go ahead, Evgeny.
In your simulations, do you see any sort of saturation in the amount of energy contained in accelerated particles? Is it still growing up to the very end, or you see that it stops growing, the total energy, I mean?
So thank you. That's a very, very good question. It's just what I could not discuss here. It's the fact that in particular in cell simulations, let me play that movie again, where they do see some saturation, which is not captured by my model here. And this saturation is related to the fact that when the Lorentz factor of the particle reaches a value of, say, 1000 in that simulation, then the gyro radius of the particle becomes comparable to the Corian scale of the turbulence. Because it becomes comparable to the this Corian scale of the turbulence, the acceleration rate drops down pretty fast. That's what I mentioned earlier, because the particles will decouple from the turbulence. And that means that you will form sort of a pileup at this energy. So you will see it now when I play the animation. So we'll see that the power law hardens in time, but then once the maximal energy has reached that point, say a factor of 1000 to 2000, then it sort of stalls, and the acceleration beyond that point becomes very slow. And you see that the particles, the power law doesn't change much here. Meanwhile, you see that the mean of the distribution continues to move in time, because I'm talking about a driven turbulence. Driven turbulence means that I keep injecting turbulence energy inside my plasma. In that case, I will keep heating my particles. If I were doing, like Comiso and Cironi, if I were doing a decaying turbulence simulation in which I input some turbulence at the start, but I do not inject turbulence at later times, then that peak here would freeze at some initial value and it would not move. The power law would develop, it would stall once the particles reach the confinement energy, and that would be it. But the last thing I would like to add is that there may be an effect here which is related to the dynamic range of the particle in cell simulation. Because if you enlarge that dynamic range, so you separate the thermal peak from the confinement energy, then what happens on the intermediate time scale may be more subtle than what is seen in those simulations.
Pasquale,
So
Blasi?
Hi, Martin.
Hello,
Perhaps as a completion of the previous question. So the one that you just described is, I understand, is more like a finite size of the accelerator criterion. But since the spectrum is so hard, I assume this 3 refers to the slope in momentum space, right? So the energy is contained in the highest energy particles. Do you expect at some point, okay?
Yes, so sorry if I wasn't clear enough. This is dn over d gamma. So -3 is not hard spectrum, it is a soft spectrum. So this is not for the distribution function. This is really dn over dp.
Okay. So this is
goes like
p
to the -3. Yes.
Okay.
So it's pretty soft. So most of the energy is here.
It's in the low part. Here. Okay. Thank you.
Sure.
Evgeny, did you have a comment? I thought I heard your voice.
It's not a comment. I think that I understand the answer of Martin, but just to make sure that I really understand it. If I got correctly, then the situation is like this. You see some development at the high energy tail, which is kind of obvious because you have to wait longer time. But at some point, you don't see, you start to see less and less development at the lower energy range. And basically, one of the aspects of my question was, is it kind of non-linear effect that you see the back reaction from accelerated particles onto the system, or it's something else? Is it related to the simulations, or is it related to the physics? I'm not clear now.
No. It's just I need to think a little bit. I'm not sure I would expect a back reaction from those high energy particles on the turbulence because they take away a small fraction of the energy. I'm not sure that you can say that nothing happens at low energy. So let me play again that simulation. You will see the peak. As long as I drive the turbulence, the peak will move to the right. So I keep injecting energy into the plasma. I hit the plasma. And if I were to do it for a longer time, it would just keep on doing it. I should say that when you do those particle in cell simulations, driving the turbulence is not an easy process. And when people say that they drive the turbulence, it doesn't mean that the way you drive or the rate of energy injection is the same at all times. Because the way you inject particle energy at as a function of time is through a stochastic process. And so you cannot fully control it. So it may very well be, maybe your visual impression here is it may very well be that that you think that the drift is very slow here because for some reason the energy injection was not as efficient at late times as it was at early times. So does that answer your question?
Yes, thanks.
Liu?
Okay. Hi, Martin. I have two questions. So one is in this plot, the y-axis is E, D, and DE, right? So this represents the particle number. So I'm wondering why, in this Kuznets theory case, the amplitude decreased, because this means the particle, the number of particles decreases a lot as it accelerates.
Sorry, I didn't get quite your question.
Okay, so I mean, when you plot this in this plot, so y-axis means, it's E, D, and E, or gamma, D, and D, gamma, right? So yeah, this is like shows the number of the particle in the total the number in this spectrum, right?
Right.
So then I'm wondering why in this dotted curve, as particle being accelerated, the number of particles decreases with time. So because initially the height is the same, the amplitude is the same with this red curve, right? It means they have like same amount of particle in the simulation. Then as time goes, it decreases.
Yeah, that's a good point. I should check maybe related to the normalization I chose here for the two. So
okay.
I think in principle they are normalized to the same. Yeah, I can check. I will let you know.
Okay. Then my second question is that since you said this Fock-Planck approach does not apply here, so so is this this Fock-Planck approach works for the spatial transport?
Well, so that is another issue. So I don't have a good answer to this actually. So it depends. So are you talking of Fokker? I mean, a diffusion equation with a spatial diffusion coefficient, or a pitch angle diffusion?
The spatial diffusion coefficient. So because it seems according to your simulation, the Fock-Planck approach does not work in this transport in energy space.
Yes.
So I'm just wondering, does it also have problem on this real space transport? in spatial transfer.
Yeah, for spatial, so I would expect that maybe for momentum diffusion, we would have the same issue with the Fokker-Planck diffusion equation, because of course this is related to the scattering time. You see, the reason why the Fokker-Planck equation fails here is that because the Fokker-Planck equation, to be valid, it will need to work with a noise, formally speaking, with a noise which is Gaussian and of infinitesimal correlation time. This is the basics of the Fokker-Planck equation. And what intermittency does here is that it kills both the Gaussian nature of the noise, which is not Gaussian at all, but also the fact that the correlation time of the noise is not infinitesimal, because the mean free path to interaction is large. Therefore, on the intermediate time scale, you cannot say that this is a small time scale. So this is why it fails. So I would expect that the same would apply to pitch angle diffusion. Now, when you talk in terms of spatial diffusion, you assume much longer time scales. And the nature of those random walks is that when you go to time scales that are much larger than the interaction time scale, then because of the central limit theorem, you should converge toward the Gaussian result, which is precisely this Fokker-Planck type equations. So, and this is what we see here. You see on very long time scale, we converge in terms of the core towards this Fokker-Planck type solution, except that we preserve a power law tail. But I would expect that for spatial diffusion, it should recover the same. Maybe I should add the transparent that I skipped, which is the following. And this is the fact that these people, Wong and Uzdensky and others, they measured in the particle in cell, they measured the diffusion coefficient, and they also measured the advection coefficient. And they say that if you use this extended Fokker-Planck equation, then you can recover or reproduce the spectrum, and they show that they can reproduce the spectrum that they see. And this advection coefficient, which is written here by the green dots, is measured from the simulation. The thing is that you see that it is sort of tailor-made to reproduce the results of the simulation. So what we are lacking here is an explanation from this non-trivial advection coefficient. So when I said that the Fokker-Planck treatment fails, I would say that the standard Fokker-Planck equation fails. But if you were able to have a more complete, or maybe with you see a more extended Fokker-Planck treatment, you could recover these effects.
Okay, thank you.
Okay, Maxim has reappeared. Maxim, could you please ask your question?
Hello, can you listen to me?
Yes.
Yes.
Yeah, okay, good. So the question is following. How many particles per cell do you have in your simulations? And probably...
So that one has 10 particles per species per cell. And each cell is the resolution of the simulation is 1/10 of the skin depth. And this is the skin depth of the cold plasma, so it's significantly smaller than the skin depth of the relativistic plasma.
And for such kind of simulations, maybe a higher number of particles could be useful, at least for checking. Because
yes,
here it looks like some kind of numerical resistivity present in the results.
So we do not. So one thing that we do instead of using a larger number of cells is that we have tried several simulations with different filtering procedures for the currents, and that doesn't affect in any way the result that we show. Maybe because we you see when I plot this, I take the average over so many particles that differences are just erased. But we do not see any dependence on this. I should say that maybe where is it? Yeah. In those simulations, so our simulations are rather modest compared to those simulations shown in those papers. So you should refer to those papers where I think these issues are discussed in depth, and they do not see any effect really of the number of particles per cell.
Does anyone else have a comment about this? Any of the people that do those simulations? Jonas, do you have a comment on this? Okay.
Hi, sorry.
Jonas, do you have a comment on this?
Yeah, I think PPC, like 10 particles per cell per species, is okay. I think I tested up to 256, but the only thing that changes is the high energy tail. So you get better statistics.
Yeah.
Okay. Are there any other questions or points of discussion that people would like to bring up?
Can I ask a question?
Of course.
Yeah, Tony Bell here. Yeah, I mean, the ratio of the Larmor radius to the K of the turbulence is obviously crucial, and I'm sort of lacking a bit of a sense about how the particles getting accelerated at high energies or low energies relate to the characteristic K of the turbulence. I'm wondering whether it might not be worth showing some spectra of the turbulence as well, so we can see where the energy of the turbulence is, whether it's at low K or high K.
Okay, so regarding the, I don't have a spectrum at hand, but again, you can find them in those papers. And it's very typical of MHD turbulence simulations that they have this K to the minus 5/3 spectrum, roughly. So that means that most of the energy, those simulations, they are really designed to inject energy at the larger scales, and they try to make this ratio between this scale of injection, so the stirring scale, and the dissipative scale as large as possible in order to probe the physics of MHD type turbulence at the largest length scales and not to be dominated by kinetic effects. And I think, as far as I understand, they are successful in doing so. And even with that type of simulation, so here for that simulation, the coherence length scale is about 300 skin depths. So the ratio of coherence scale to skin depth is about 300. So, and most of the energy then is contained on the larger scales. So maybe that's more apparent in here. So you have a view of an illustration of this. Then regarding your question, I did not discuss this because I don't have time, but really the relation of the Larmor radius to the coherence scale is an important issue. But from those particle in cell simulation, there is not a clear indication that it plays such a role, meaning that once the Larmor radius is significantly smaller than the scale of the turbulence, it seems that nothing special happens on whether it's 10 times or 100 times smaller than the scale of the turbulence. And the fact that usually people really pay attention to the location of the Larmor scale among the scale of the turbulence because they have in mind resonant wave-particle interactions. But in those types of turbulence theories, you do not expect those resonant wave-particle interactions. And that's because, so it's a bit of a complicated story. Let's say that for Alven mode, the physics of the cascade makes them to be, in terms of linear wave cascade, linear wave properties, makes them to be highly anisotropic, and that kills the resonances. Which is why maybe the physics of particle acceleration in that type of environment is not dominated by wave-particle interactions or resonant wave-particle interactions, but really the particle get accelerated because it is just sensitive to all the scales above its Larmor radius. And therefore, as long as the Larmor radius is small enough compared to the coherence scale of the turbulence, the particle will be able to feel all this power on the larger scales, and it will get accelerated from this. Now, whether the physics of acceleration strongly depends on the scale of how far deep in the inertial range you are, I cannot say really at this time, and I don't think that the particle in cell simulations really can, because you would need to reach some very large dynamic range. So.
Thank you. You've confirmed that this is a complicated subject. And I'm not surprised that Fokker-Planck doesn't work. The question really is whether there's some straightforward way of doing it, which is manageable without doing full pick simulations.
That's right. Yeah, I agree.
Okay. Do people have other questions or points of discussions, comments?
Hi, everybody. I'm Luigi Costamante here.
Hello, Luigi.
Hi, happy to see all of you again after some time. Just a quick question. Have I understood well about the absence of pileup? That it is something that happens only in the intermediate state, or it's a temporary effect that some pileup might develop before going on a smooth power law. Is it correct, or can you?
So maybe let me. So I would say that so when I say pile up, I have in mind this spectrum in dotted line that shows that most of the energy is contained at a location that moves in time. You see, this is the mean here, moves in times about as fast as it diffuses, as it broadens in time. So this is this notion of a pile up here.
Okay.
And you see that what is seen here is that the drift of the distribution is very slow because it is related to energy injection. So this is where there is no pileup.
Yeah, it remains really in, observationally, it is something still connected, let's say, with the shift of what was the initial thermal core, basically. I mean, you have accelerated all the particle. It shifts at slightly higher gammas, but very, very slowly. Correct?
So sorry, say that again. I'm not sure I understood what you mean.
Sorry. So that basically the shift of the maximum energy shifts very slowly with respect exactly to the Fokker-Planck. Okay, and it remains at low Lorentz factors.
Yes.
10, 20.
Oh, okay. Yes.
Okay.
So I would say take something maybe more concrete. So, for instance, a turbulence in one of your blazars. So
no, I'm still trying to connect this with some observational features. So
yeah. But let me connect it with your scenarios, your prototypical one. So if you have this simulation here is for a sigma of unity. And we start, so it depends also on the initial temperature. So initially, the temperature is maybe a gamma of 6 or something, mean energy. And then if the sigma is of unity, that means that the quantity of energy that you can transfer to the plasma is, you can roughly double its energy if you transfer the turbulent magnetic energy to the plasma. So you would shift this by a factor of 2. This is what it says. This is how you should understand the drift. Now, it depends also on for how long you inject energy into the plasma, because this is really an injection rate, right? So if you keep energy, so it depends on if you want, on the reservoir of energy that you can spend on your plasma. So that will give you the amount by which you should shift the peak of that distribution. But then the power law should extend all the way to the confinement or to the radiative cutoff energy.
Okay.
And so the meanwhile, I mean, if I had a huge range, a huge dynamic range, my pileup distribution would just keep shifting all the way towards the confinement energy, which would violate energy conservation.
Yeah, of course. Okay, thank you.
Sure.
Andrew Taylor?
Yeah, just a quick query for understanding. You were saying, Martin, that your diffusion coefficient, momentum diffusion coefficient, went like p², sort of hard sphere type scattering going on. So that's why you've got log parabola for your comparisons in your quasi-linear theory. So I was confused because you said to Tony's answer that your magnetic field spectrum, power spectrum is going like 5/3, I think. So it's, you know, Kolmogorov type diffusion. And there, you know, if I've got, normally have that relationship between spatial diffusion coefficient and a momentum diffusion coefficient. I don't understand how, why you call upon quasi-linear theory with log parabolas when if I had Kolmogorov turbulence, you don't get log parabolas.
Yes, so that's because you have quasi-linear theory in mind, Andrew. And
yeah.
So in that case, the diffusion coefficient would be going like 2 minus q, right? So
yeah.
Basic,
I'm not sure why quasi-linear theory with log parabolas is the reference model. I guess that's my question.
Yes. Okay. So it's a lack of details on on my part. It's the fact that in those simulations, people have measured the diffusion coefficient, and the diffusion coefficient actually is what I show maybe later is p squared. So this is here. They do measure a diffusion coefficient like p squared. So in order, and this is the same simulation roughly. So we use this p squared.
Sorry, but it goes like p squared when you're above the resonance scale, right? You said that below it, it doesn't.
Oh, so well, okay. So if you want the details, it's yes. If you're inside the inertial range, it's p squared, and here there is a different dependence. So what is plotted here is the spectrum. So you see, when you are close to the thermal core, you have a different dependence, which is likely related to the influence of parallel electric fields. So really, when you're in the non-thermal tail where Fermi acceleration plays a role, this is p squared in those simulations. So for that reason, to make this plot, we used p squared, and then we use the solution for p squared. But indeed, as you said, the spectrum is minus 5/3. But you should keep in mind that when you relate this spectrum of minus 5/3 to this 2 minus q coefficient of quasi-linear theory, this is really an idealized model in which you have truly resonant wave-particle interactions. And so when you consider more extended theories, so in which you include resonance broadening, because as I said to Tony, you lose the resonant character of those interactions. So when you account for this resonant broadening inside quasi-linear theory, then you also lose the 2 minus q. And as a matter of fact, this DPP going like p squared is a generic prediction of those quasi-linear theories that include resonance broadening due to this time damping, AD damping effects and so on.
Okay, that's quite clear actually, thanks.
So this p square has nothing to do with the anisotropy of the turbulence. The fact that for aphanic turbulence you lose power in the parallel modes.
So in my view, no, because I don't think that quasi-linear theory applies here.
Well, but it could well be that it's just you don't have power on those modes, on those scales, and therefore quasi-linear theory, you should be applying quasi-linear theory to the power spectrum in the parallel modes, which, however, is suppressed. It could be true what you're saying, but it's not obvious, right?
Okay, I'm not sure. I'm not sure I get your point.
The k to minus 5/3 applies to a three-dimensional homogeneous isotropic turbulence,
true.
right?
That is
so
true.
If you lose power in the parallel modes, then in principle the rate of scattering could go to 0, right? So it's at some point it might even be that you get something very fastly scaling with energy just because scattering is very suppressed by the lack of scales.
Ah, I see. Okay, so so in those simulations, they, if I remember correctly, I think it's a paper by Zdenkin and collaborators in 2018, where they analyze in detail the properties of the turbulence, and they do the decomposition into parallel and perpendicular space, and they do observe some anisotropy, typical of Goldreich-Schrieder theories.
Mm-hmm.
So for this is that was part of my reply to Andrew, is that in that case, again, if you use quasi-linear theory, idealized quasi-linear theories with that anisotropic spectrum, then as you say, the rate of scattering goes to 0. but the idealized quasi-linear theory should not be applied in that configuration, because in those configurations, you're in a strong turbulence, meaning that the eddies, they interact on their time scale, and therefore you cannot consider them to be infinitely long-lived. So the least you can do is to account for their finite lifetime. Then if you do so, again, in the framework of quasi-linear theory, but accounting from this eddy damping, then that would actually broaden the resonance, and that would bring back some scattering. And then this is what Chandran showed in 2000, is that in that case, you would recover a typical scattering time scale, which is of the order of the coherence scale of the turbulence. And therefore, a momentum diffusion coefficient going like p squared.
Yeah.
So hard sphere regime.
Just to be sure that I understand, if you applied all this to non-relativistic turbulence, so that the condition on the evolution of the eddies on long time scales would fail, so probably the disagreement with what you call quasi-linear theory would probably be less evident, right?
No, it gives exactly the same result, as a matter of fact.
Mm.
Okay. I guess one last question, comment, or a point of discussion.
Can I ask one? To what extent are nonlinear effects important? In other words, like with standard old shock simulations, it's the relativistic particles that are generating waves and changing the scattering coefficients. And if you have anisotropies in the plasma distribution, you can also have their instabilities that can change energy and distribute and create waves. So to what extent are waves generated by the non-thermal particles important in this case, say in the PIC simulation? So you can't really do it right without actually taking the non-thermal particles into account, even for this case. Is that true or not true, you think?
Well, that's that's a tough question, Paolo.
Yeah.
I think it's the whole process of turbulence, right? It's this nonlinear all-time interaction between particles and waves, so and the eddies. So in no way in those particle inside simulations, in no way the particles are test particles. I mean, they do control the development of a turbulence. Now, whether you can break up or isolate the contribution of the particles in the wave generation process, or maybe say on some scale they generate some small scale instabilities that will contribute, and this is very difficult to say. There is some evidence that instabilities like mirror and fire hose do play a role in controlling in regulating the anisotropy of the distribution functions of those particles. So to answer your question, I think it's yes, you do expect that the particles interact with instabilities in those turbulent environments. So, but I would say that unlike you see the shock, when you have a shock wave, the physics of the shock is controlled by at least the immediate vicinity, or the transition layer of the shock is controlled by the thermal particles. And then you have those non-thermal particles that propagate on longer time scales. And then you have, you can do maybe some nonlinear shock theory to try to see how they modify the environment of the shock. But here they're all in the same place, in the same spot. So
yeah. But just one thing, but your first thing you discussed was a test particle, your d gamma dt, that's a test particle approximation. So that works at some level? Or?
Absolutely, yeah. Or that's, I don't know, maybe you can view that as a mean field approximation.
Okay, thanks.
For shock, it's complicated, but for turbulence, it's not that bad, right? I mean, in the sense that when you have a cascade, you have, especially if you cool the plasma. If you cool the plasma, then you have more or less force-free with some damping. You have more or less force-free turbulence cascade with some damping, which is of course kinetic, and then there is a full feedback of particles there on small scales. But the development of the turbulence is not sensitive to the details of particle kinetics.
Okay, what kind of damping do you have in mind?
Well, that depends on well, for example, Landau damping, but it's not. I just wanted to say that you have turbulences can be clean in principle on small if the damping occurs on small scales mostly.
Oh, okay, I see what you mean. So okay, I see.
Yeah, of course, when you have more
So
particles that engage in larger and larger eddies, then they can drain a little bit of, because the energy they gain is from large scale eddies, so they drain a little bit energy of the turbulence. But yeah, but it could be mostly on small scales.
yeah, so you're separating a fluid or MHD from a kinetic picture. Is that what you're saying? Okay.
And maybe to continue on this point that Paolo asked, that turbulence is still what we typically study magnetically dominated. So it is automatically, you mean that the magnetic energy dominates from the particles. Particles cannot influence the plasma so easily. And then another point is really what Andre also said about that we can do radiative cooling, which really prevents the formation of these non-thermal particles. And then you still see the same kind of spectra for the magnetic fluctuations, for example, and the turbulence decays similarly. So I think this is a good implication that the high energy non-thermal particles do not actually take part in the cascade process itself.
Thanks.
Okay.
Thank you.
I think it's
Yeah, we better stop maybe. Yeah.
I think it's time to wrap up. I want to thank Martin for a very nice talk, and in particular for making this talk kind of accessible and pedagogical for a broad audience, but interesting enough also for specialists. Okay, thanks very much, Martin.
Thank you.
Yeah, it's a model talk, Martin. That's how everyone should give talks in this series, I think.
Yeah, agree. And I guess we will see everybody in a couple of weeks. Okay, bye everyone.